which is the basic antenna and which is a fictitious antenna, because it is extremely difficult, almost impossible to get a actual Hertzian dipole or two electrons which are oscillating and which are separated by an infinitesimal distance. So that type of dipole is not practically feasible, but that is the basic of all other antennas. Any antenna that we consider, for that we can assume that the antenna consists of many Hertzian dipoles. So many Hertzian dipoles are connected. So Hertzian dipole is an elemental length. So if you connect those elemental length along a line, then you will get a linear antenna. So and find out the fields for Hertzian dipole, integrate that over the length. So dE will be the field for Hertzian dipole. Then integrate the dE, that will give you the field for a linear antenna. Now, when we consider the linear antenna, the most common linear antenna is the half wave antenna. How do you get a half wave antenna? We have already discussed this. Instead of saying half wave antenna, we just said that if we consider a transmission line and we consider folding it at its two ends, then we get an antenna, a radiating system. And we explained how radiation comes out of a transmission line which is folded at its two ends in opposite directions. If we fold both the wires, one in upward direction, one in downward direction, or one to the left, one to the right, or in any two opposite directions, exactly opposite directions, then it starts radiating. Now, on the transmission line, the voltage is distributed, the current is distributed. So, consider the transmission line end as the open transmission line. So, we have not put any load. So, the transmission line is terminated in an open circuit. If it is terminated in an open circuit, then at the end, the current at the terminating end, what will be the current and what will be the voltage? The voltage will be maximum, whereas current will be minimum. Then next point where the current will be minimum is after a half wavelength. So from there it has to come to half wavelength, then the current will be minimum. Where the current will be maximum, when the current will be maximum is when you come quarter wavelength. So current will be maximum if we come quarter wavelength from the terminating end. If we come towards the non-terminating end or towards the source a quarter wavelength, the current will be maximum, and at the terminate end the current will be minimum. So if we hold the transmission, if I want to feed maximum power, then I should have maximum current. And therefore, if I fold the transmission line at a point where it is having maximum current, so that will be a quarter wavelength from the terminating end. So suppose the transmission line is parallel to x-axis, then we'll fold one of the positive line or the upper line, upper wire in the along the y-axis at a quarter wavelength. Similarly, the lower wire will be folded in the negative y direction at a quarter wavelength. Since it is folded at quarter wavelength, at the center, at the folding point, the current will be maximum, whereas at the two ends, the current will be minimum. Now, because of this, total folded length is, for the upper wire it is lambda by 4, for the lower wire it is lambda by 4. Therefore, total is lambda by 2. Lambda by 4 plus lambda by 4, that is lambda by 2. So that is how we get a half wave dipole. This is called a half wave dipole antenna because the analysis, this half wavelength of folded transmission line can be used and can be analyzed by considering this half wavelength as a combination of many Hertzian dipoles along the length. So this is a half wave, this is like a dipole which contains many Hertzian dipoles. So we consider this half wavelength and we integrate the Hertzian dipole or fields due to Hertzian dipole over this length to get the field of this half wave dipole. So this is what is a half wave dipole and why we go for half wave dipole. Because if we go for half wave dipole, we assume that we can give maximum power to the dipole. So maximum excitation with maximum current or maximum power is possible. Therefore, we consider half wave dipole. So that is the basic antenna. Now the basic antenna will be a half wave dipole. So we'll start with a half wave dipole. In this lecture, in today's lecture, we are considering, we're going to discuss about what is a half wave dipole. Okay, and the outline of discussion is we will start with what is called the source and what is called the observation point. This we have seen already for the Hertzian dipole. Again, I will discuss it or revise this part. What is source and what is observation point? Then we'll consider what is current source. Then we know what is vector potential. Then we'll find out general expressions of fields, radiated field, and a problem set, a set of problem that you have to work out. We'll discuss a set of problem. You will work out that at your home. So this is what we are going to discuss today. So let us consider what is called a source point and what is called an observation point. So this here you see, I have drawn a picture. Look at this picture. From the origin, we have a position vector r dash, and at the position vector, we have got a source. So this source is enclosed within a volume V dash. So V dash encloses the source. R dash is the position vector of the source, and within the enclosed volume the current density is J. So that is what is the source point is R dash. So if it is distributed current, or if the current is homogeneously distributed over this volume, then the center point of this volume will be R dash. That is what we will consider as R dash. Then we have a field point P whose position vector is RP. RP is the position vector of a field point. Why we call it a field point? It is actually an observation point where we are going to observe the effect of the source. Because of the source there is a current J, current density J. The effect of current density J, we are going to observe at an observation point, and the effect of current is creation of an electromagnetic field. A time-varying current creates an electromagnetic field. Therefore, we will probe for field at a distance point, at a far field point, and that is called the field point or the observation point, since we are considering the effect of the current source or the source, and the effect is the field. Therefore, the observation point is also called the field point. So we have the position vector of the field point RP, position vector of the source point is R dash, then the vector which is connecting the source point to the field point. So from the source point, it is directed towards the field point. So the vector connecting the field point to the source point is capital R. That will be equal to, since you know what is vector, this is a vector diagram. R dash, Rp and capital R form a vector diagram. In this vector diagram, R dash plus capital R is equal to Rp. Therefore, you can say capital R is equal to Rp minus R dash. So this is how you represent the source point and field points using vectors, and when the origin is at some reference point. This origin, if we take this origin to the point r dash, which means we make r dash 0, origin coincides with the source point, and then r dash is equal to 0, then we have capital R is equal to Rp, and that is a special condition. But general condition is the source, for the source we have a vector r dash which represents its position vector. For the observation point we have a vector Rp which represents its position vector, and the vector from the source to the observation point or field point is capital R, which is equal to Rp minus R dash. So we'll start with this. Now let us look at a half-wave dipole or a current element. So the current element, here the current element is aligned to the z-axis. The axis of the current element is aligned to the z-axis. We are considering an infinitesimal length or elemental length delta z along the current length, along the current element, and the current through this elemental length is I. Then current is along the z direction, so that is what we saw. Then observation point is P, and the distance to the observation point here from the origin, the center of this current element is at the origin. The distance to the observation point from the origin is equal to small r. The distance to the observation point from any other point on the elemental length is capital R. So we see this. Now let us establish some relationship. Now you can see the same picture that I have shown you earlier, and in this picture what we see here is the vector to the observation point. As you know, capital R here, delta Vd V dash is the elementary volume which is enclosing the source. R dash is the unit vector, R dash is the position vector of the elementary volume dV dash. Then from the point R dash, we are going to the observation point. Observation point P is in the far field, which for all practical purposes can be assumed to be at infinity. So it is at an infinity distance from the origin and from the uh, source point. Since it is at an infinity distance or equivalent to a very large distance, if we connect the origin to that point and the source point to that point, they can be parallel. As you know, two parallel lines, they meet at origin. So what we do here is we take a point, far field point P, and there we draw a line which is perpendicular to the line, which joining the origin or joining the source. And so that is the dashed line here at the point P. Dashed line here is perpendicular to capital R and small r. That indicates that the capital R and small r are parallel, and at a large distance they will meet. Okay. And now back. Now you can see that small r and r dash, the angle between small r and r dash is alpha. That is the angle. Now, if I drop a perpendicular from the elemental volume onto small r, then that will meet it at a point which is at a distance r dash cos alpha. Because if I drop a perpendicular, then r dash and the perpendicular from the dv dash volume onto r, and the point where it meets the vector r, that forms a right angle triangle, and the base of that, the angle connected to the base is alpha. Since angle is alpha, hypotenuse is r dash, therefore base will be r dash cos alpha. So from the origin it is at a distance r dash cos alpha. Since it is at a distance r dash cos alpha, we can easily say that this small r is equal to capital R plus r dash cos alpha. R dash cos alpha also you can say that r dash cos alpha is equal to r cap dot r dash. That you can say. Why r cap dot r dash? You know, the dot product of two vectors is, if we take AB, then it is AB cos theta. So r cap dot r dash will be r dash cos alpha. Because the angle between r and r dash is alpha, therefore r cap dot r dash is equal to r dash cos alpha. So capital R is equal to r minus r cap dot r dash. Now why capital R is equal to r minus r cap dot r dash? What we have done here is, we have two parallel lines. One is from the origin, one is from the volume, and we have dropped a perpendicular from the volume onto the other line. From the elemental volume dv dash, we have dropped a perpendicular which meets the other line which is coming from the origin. Therefore, where it meets the other line, from that point towards infinity, their length will be same. So the capital R will be equal to small r minus the portion which is before the meeting point or which is between the origin and the meeting point. And that distance is r dash cos alpha, or that is r cap dot r dash. Therefore, capital R is equal to small r minus r cap dot r dash. Okay, next. And now let us consider a situation here, a similar situation that we discussed up to now. Let us consider a similar situation. We have a coordinate system xyz. We have an observation point on the yz plane, which means x is equal to 0, and it is on the yg plane or x plane. Therefore, x is equal to 0. So the observation point P is equal to P. Its coordinate points are 0, y, z. Now, that observation point is has a position vector small r, or and the distance of the observation point from the origin is smaller, and the distance of the observation point from a distance z dash on the g axis from the origin. So when z is equal to z dash, from that point, if I consider the distance of the observation point, that is capital R. Now what we will do is, from the position z dash along the z axis, from that we draw a line which is parallel to y-axis. Then we drop a perpendicular onto that line, which is up from the observation point P. So observation point P, we drop a perpendicular line which meets the line parallel to y-axis drawn from z dash. Now if that happens, then the meeting point, at the meeting point, the y coordinate will be y, because the y coordinate of P is y, therefore the meeting point will have y. Since that line is perpendicular to the y-axis, so along that line, perpendicular line, everywhere the y value will be y. So that is that. Then for perpendicular line, for the observation point, the z coordinate is z, and it is at a distance that is meeting the line at a point uh, uh, which is z minus z dash. Why it will be z minus z dash? Because if I draw the line, extend the line from P onto the y-axis, then where it meets the y-axis, that distance is z. But where it meets the parallel line to the y-axis, that distance from the y is z dash. Therefore, this distance will be z minus z dash. Now, let us find out what is r dash in this case. Okay, next. So, in this case, since we are considering a point z dash, for that, that is the source point. If you consider the source point to be at z dash, then r dash is equal to z dash into z cap. Then r will be, r, the position vector is 0 y z, therefore r is equal to y cap plus z cap. So we have got the two vectors, r is equal to y cap plus z cap, r dash is equal to z dash z cap. Then what will be r square? R square will be y square plus z square. What will be z? Z will be, if this angle is theta, angle between the z axis and the vector r is theta, then z is equal to r cos theta, y is equal to r sin theta. So we know these things already. Then what is capital R? Capital R vector is equal to small r minus small r dash. So that you can write as small r dash is equal to z minus z dash into z cap small r is equal to y cap plus z cap. Small r dash is equal to z cap z dash. So rearrange that, take y terms one place and z terms in as one term. So capital R will be y cap remains as it is plus z minus z dash into z cap. That is what is capital R. Then what will be the magnitude of capital R? This will be y square plus z minus z cap square root of that. So capital R is equal to square root of y square plus z minus z cap square. So that you can write as, expand it, that will give you square root of y square plus z square minus 2z dash plus z dash square. That will be what is capital R. So let us rewrite that. If we rewrite that, that is equal to y square plus z square is equal to r square. So that part is r square plus 2z dash, that we can write as 2r cos theta, because r cos theta is z. So from that we can 2r cos theta, 2 remains as it is, z dash for z we can write r cos theta, z dash remains as it is. Therefore this part will be minus 2r cos theta z dash, then z dash square remains as it is. So z dash square remains as it is. So r can be written in this form. Capital R can be written in this form. Okay. And now let us expand that. capital R. When we wrote that, let us expand that in using binomial coefficient. So if we expand that using binomial coefficient, it will be r square to the power half plus 1 by 2 r square to the power minus half into minus 2r cos theta z dash plus z dash square plus 1 by 2 into minus 1 by 2 r square to the power minus 3 by 2 into 2r cos theta z dash plus z dash square whole square plus other higher order terms. This is using binomial expansion for capital R that we saw, or the magnitude of R that we found out in the previous slide. So just simply expand it using binomial coefficients. Now if you relook at it, r square to the power half is r, 1 by 2 r square to the power minus half is equal to 1 by 2 r. So that will be half r. So 1 by 2 r, that into minus 2 r cos theta z dash. So my numerator 2, denominator 2 will cancel out, minus will be there. Then r in the numerator, r in the denominator, that will cancel out. So that will leave out z dash cos theta. Then plus z dash square sin square theta by 2r plus z dash cube sin square theta cos theta by 2r square plus other higher order terms. Okay. Also for this type of distribution or orientation of a field, we will get orientation of a source, we will get what is capital R in this form. Now let us come to the current source. This current source that we are going to discuss is about the half wave dipole antenna. Half wave dipole antenna, as I told you, is one of the most popular antenna, both for modeling a building block and in direct application, both. This can be applied directly. People use half wave dipole antenna directly. Also it can be used as a modeling block for other antennas. This is the half wave dipole antenna. The half wave dipole, as I told you, is realized with a straight wire fed in the center, with a pair of straight wire which are fed in the center, that I told you in the introduction. A simple and accurate model for the half wave dipole antenna is a linear current that we are going to feed. So look at this picture. In this picture, we have a wire. You can see the current is I1 in the upper wire, current is I2 in the lower wire. I1 is folded upward, I2 or the lower wire is folded downward. I1 is coming from left to right, I2 is going from right to left. Now if I1 is equal to I2, then the current distribution on this wire will be shown like this. This is the current distribution. But if I1 is greater than I2, then the current distribution will be distorted, and you can see the new current distribution will be in this form, where now you can see the amplitude of I1 is more. So I1 is above the folded part, is above the lower folded part, because lower folded part has lower amplitude, upper folded part has higher amplitude. So that will be like this. Then the second one, I1 is greater than I2. Similarly, for I2 greater than I1, you can get, just reverse it. Lower part will be above and the upper part will be below that. Now this type of antenna, when I1 is not equal to I2, that type of antenna is called an unbalanced antenna, unbalanced feeding. That type of feeding to the antenna is called unbalanced feeding. When I1 is equal to I2, this type of feeding to the antenna is called balanced feeding. So either you can have a balanced feeding or you can have an unbalanced feeding. We are concerned here with balanced feeding. So in this case, what we are doing is we are looking at a half wave dipole antenna. Therefore, length of the current element is lambda by 2, which is the last figure on the right hand side. So length of the dipole is lambda by 2. As we discussed earlier, along the length current will be distributed. At the ends the current should be 0. Theoretically it should be 0, and at the center it should be maximum. So at the center we have the maximum current, therefore at the center we have Im. As you go away from the center towards the end, then the current becomes goes from Im maximum to 0. Gradually at the end it becomes 0. Therefore Iz is the current which is varying along Z. So Iz will be Im. This you can see like a sine wave, half wave of sine wave. So this will be Im sine of k lambda by 4 minus absolute of Z. This is the distribution, current distribution, where Z is less than equal to lambda by 4. So for the upper part or for the lower part, that is why we have taken absolute value. So Iz is equal to Im sine k lambda by 4 minus Z. What is k? K is equal to 2 pi by lambda. So you can put that if k is equal to 2 pi by lambda, it is sine 2 pi by lambda into lambda by 4. So that gives you pi by 2. So that and minus uh, 2 pi by lambda into z. So that shows that when z is equal to 0, this will be at pi by 2 sine pi by 2 sine pi by 2 is 1. So that will be giving you maximum current Im. So when z is equal to 0, you get maximum current. When z is equal to lambda by 4, then you have uh, z is equal to lambda by 4. So mod of z is equal to lambda by 4. So within bracket is lambda by 4 minus mod of z. So lambda by 4 minus lambda by 4, 0. Sine 0 is equal to 0. Z is equal to lambda by 4 at the ends. Therefore, Iz will be 0 at the ends. And the current distribution is sinusoidal. So this describes us the current source. This is how we get what is the current. Now, we have to find out the fields due to such a current distribution. To find out the fields, the first step is we have to find out the vector potential. This is the easiest method, is find out the vector potential for a given current distribution. Now we know what is the current distribution, and we know already the expression for vector potential when the current distribution is given to us. The expression for vector potential is equal to 1 by 4 pi integration of mu j r dash exponential minus j k dot r, capital R, and divided by capital R integrated over volume enclosing r dash. So that is what is the vector potential. So now let us put what is j r dash. J r dash is equal to I z dash delta x dash delta y dash. Why delta x dash delta y dash? Because this current is along the z axis. It is not, there is no extension along x axis or along y axis. So this current exists only when x is equal to 0, y is equal to 0. Everywhere else it is equal to 0. Everywhere else on the x-axis along the x or along the y, it is 0. It exists only when x is equal to 0 and y is equal to 0, which is the z-axis. And on the z-axis, it varies as iz dash, and we have seen what is ij dash. Then we have mu. Mu we have taken outside. 4 pi cap, 4 pi remains as it is. The current is z direction, therefore we have z cap. So outside we have z cap, mu by 4 pi, integration of delta x dash, delta y dash, then ij dash that we got from j r dash, then exponential j k dot capital R, and we know on the expression for capital R. So from that, if we put that exponential minus jk into k cap, k vector is equal to k into k cap, and capital R is equal to R minus R dash. So we put that dot R minus R dash. Then in the denominator we have capital R, which is equal to R minus R dash. So we put R minus R dash in the denominator. Then the volume element is dx dash, dy dash, dg dash. The volume element enclosing the source. Source is given by R dash. The point of the position vector of the source is R dash. Therefore, the volume element is dx dash, dy dash, dg dash. Now integration and delta x dash dx dash is equal to 1. Integration delta y dash dy dash is equal to 1. When we take these integrations from minus infinity to infinity, that gives us 1. So that once you get this, then this leaves us with and z cap mu by 4 pi, integration along z dash only. So integration along on the z dash or z axis, iz dash exponential minus j k k cap dot r minus r dash by r minus r dash. Now that gives us the expression for a. So a is equal to z cap mu epsilon mu exponential minus j k r divided by 4 pi r, this we get, then into exponential integration of iz dash exponential minus j kz dash cos theta dz. So that we got. Now we will find out what is the expression for field. E is equal to minus j omega a plus something that we know. So that is minus j omega a minus of minus j omega a dot r cap, that into r cap. This we know from the for the um, time harmonic electric field. The expression for E using vector potential is this. Now this E has two components, as we have seen already. It has two components. It does not have a component along radial direction. It will have a component along theta direction, and it will have a component along phi direction for the radiation field. So this will be equal to minus j omega into a theta theta cap plus a phi phi cap. Since E has two components, so A will have two components along theta, along phi, and there will be no radial component of A. So this will give us minus j omega remain. We have taken common. Then A has two components, A theta theta cap plus A phi phi cap. Okay. So from that we get that E is equal to minus j omega sine theta az theta cap, because a phi will be equal to 0 because it is oriented along the z axis. The current element is oriented along the z axis. So the integration is rolling along the z axis, and it is symmetric in the phi. Since it is symmetric in the phi, so phi will have no contribution. A phi component will be equal to 0 because of the symmetry. So only component is theta cap. So from the theta cap, a theta is equal to, as we have already seen, a theta is equal to a z sine theta. So when theta makes the theta is the angle between z axis and the position vector or of the observation point. So that gives us sine theta az. So E is equal to minus j omega sine theta Az theta cap. Now you can find out what is H. We know the relationship between H and E. So from that you can see H is equal to 1 by eta r cap cross E. As now E is theta cap, E has theta cap, therefore r cap cross theta cap will give us phi cap. So H will be only in the phi direction. So H will be in the phi direction, E will be in the theta direction. Now H phi, H has only phi component, so H phi will be E theta by eta. So this we have got what will be the E theta by integrating the A theta. So finding out A theta, we will get E theta is equal to j omega mu, that will remain as it is, 2 Im by k exponential minus jkr by 4 pi r sin theta cos pi by 2 cos theta by sin square theta. This will be what is E theta. And let us write this cos pi by 2 cos theta by sin square theta as f theta and sin theta as g theta. Then E theta is equal to j omega mu at 2 Im by k exponential minus jkr by 4 pi r into capital F theta, where capital F theta is equal to g theta into a small f theta. That is what is capital F theta. So from that we get using this expression. So for E theta we can get the animated field for the dipole antenna. So let us look at the animated field for the dipole antenna, half wave dipole antenna. Look at the field animation here. Uh, uh, so this for a half wave dipole antenna, if you look at the left top figure, in this and the left top figure, you can see the two ends. The charge accumulation is at the two ends. The distance separation between the two ends is lambda by 2, and in this case charge accumulation is at the two ends, and you can see the charge increases and decreases. At the two ends charge is increasing and decreasing. As charge increases and decreases, the field emanates from this length of the wire that is shown in the bottom left, that shows the emanating field. On the right hand side you can see the field, clearly you can see the field which is going out from the antenna in the top one, and the bottom one shows you the antenna and the field radiating from the antenna. So the vector field is shown in the bottom figure. Top figure shows you the exact field, how the field or the energy distribution is shown in the top figure. Right top figure shows you the energy distribution from the antenna. Bottom figure shows you the vectorial energy distribution in the top antenna. Then let us look at the radiation pattern. So radiation field or the radiation pattern. So you can see here we have length is half wave length. So we have got a half wavelength dipole antenna. The pattern factor is shown in the above. You can see we are comparing the half wavelength antenna and the Hertzian dipole antenna. So Hertzian dipole is the blue length, half wave dipole is the uh, deep blue or navy blue, light blue is the Hertzian dipole. You can see that their uh, patterns are almost same. Then what is pattern factor, that we'll discuss later, but this green field that shows us a pattern factor. Now in this case, the length of the half wave dipole, if it is large enough, the electrically, if it is large, electrically large means compared to lambda. Electrical length means the length compared to lambda. So if we say that the length of the half wave dipole, it is electrically large. Okay. So if it is large enough electrically, then the radiation contribution from the current elements along its extent, along the dipole, will have significant phase variation in the far field as a function of angle around the antenna. Why this will? There will be significant phase variation. Electron length is large, and as you know, phase and path length is related to path. Path and phase difference are related. Path difference and phase difference are related. Therefore, if it has significant length, then the phase variation will be significant. Now, variation will be significant. This will be a function of angle. This phase variation will be a function of angle around the antenna due to the difference in path length from the current elements to the far field. Now, in the broadside direction means theta is equal to pi by 2, and far direction is theta is equal to 0. In the broadside direction, all path lengths are equal, and there is a full phasor addition. Full phasor addition. Because of full phasor addition, you get this type of distribution that we are seeing in the figure. And so the pattern maximum will be in the broadside direction. For other directions, if it is not broadside, so theta is not pi by 2. If it is less than pi by 2, so from pi by 2 you are going towards 0 or you are going towards pi, there is partial cancellation due to phase difference between current elements. Therefore, as you move away from theta is equal to pi by 2, gradually the amplitude tapers down. That you can see here, either towards 0 or towards 180 degree. The the amplitude is tapering down. As you go to the end fire directions, then it is equal to 0. Theta is equal to 0 or theta is equal to 180 degree. It is 0 or it is minimum. So this distribution you can see from the blue lines. Okay. And now this distribution is f theta is almost like a sine theta directions, which is 0 at theta is equal to 0, 0 at theta is equal to 180 degree, but it is maximum when theta is equal to pi by 2. So on the variation of the field is almost like a sine theta variation. It is not exactly sine theta, but it is like a sine theta variation. As we have seen, E theta is capital F theta, which is G theta into small f theta. G theta we have seen it is sine theta. Therefore, this variation is sine theta variation is already embedded in this, which is this is what I wanted to tell you. And if the dipole length is increased beyond a one complete wavelength, it is not half wavelength, it is more than half wavelength variation, then you will get this variation to change. Gradually it will keep on changing. বুঝলে? সেটা তলব করে দিল, স্লাইডারটা। হবে না? Okay. So now with this, so we'll come to the end of this discussion. Now let me give you some problems. So on this, so now we'll come to the problems. Okay, so let's go to the problem. So the problem for solving the problems that we are going to discuss, I will give you some hints, which you already know. The hint is, okay, next. Yeah, any hint? एटी चेंज होनी एटा 23 रहिला okay so look at the hint is related to the Fourier transform and in the Fourier transform या पूर्वटा बोलो back okay the time shifting property gives us that if xt and x omega are Fourier transform of each other, Fourier and inverse Fourier transform, then xt, if you take Fourier transform, you get x omega. If that is done, then xt minus t0, if you take its Fourier transform, it is equal to exponential minus j omega t0 x omega. Similarly, for shifting frequency shifting, if you take x capital X of omega minus omega 0, if you invert it, take its inverse Fourier transform, that will give us exponential j omega 0 t into xt. Next. ସେଠି ହଉନି ସେ ଲେଜରଟା ବନ୍ଦ କରିଦେ escape हाँ देख लो नेक्स्ट करो okay so what I will do is you will use this to solve a set of problem to escape कर जा just give me a minute escape कर जा और तेरा start कर